Okay, so this is 5, 8, 14. Okay, so we had talked about Bronsted-Lowry acid. Remember, we had kind of practiced, okay, who here gave up a proton? The H2O gave a proton to the ammonia, making it an ammonium ion. So, H2O then is the what? It's the acid. So weird. Bl acid, H2O. Oh, this is terrible. So, if water gave up the proton, who accepted the proton? Yeah, the ammonia accepted the proton. That leads us to talking about Bl bases. Okay, so if we revisit our reaction from the previous slide, this we said was a Bl acid because it donated a proton. The thing that's the Bronsted-Lowry base is whatever accepts the proton. So, ammonia rather, is the Bl base. That's not so hard, is it? So the person, or the substance that gives the gift of a proton is your acid. The substance that accepts the gift of a proton is your base. Okay. Let's shrink this down and let's look at an example. So sodium hydroxide, we talked about it yesterday. What do you know about sodium hydroxide? Is it an Arrhenius base? Yes, it is. Well, let's look at it in the context of Bronsted-Lowry. So what kind of compound is sodium hydroxide? Ionic or covalent? Ionic. So this, when it goes into water, is capable of doing what? Dissociating. I know, that's so tricky. It's so hard. Okay, it dissociates, and it dissociates into what? Sodium and hydroxide. So under the Arrhenius definition, this was a base. It increases the concentration of hydroxide ions. Has it accepted a proton? No. This is not a Bronsted-Lowry base. Ugh. Because it's all functional. It's all behavioral. If it doesn't give up a proton, it's not an acid. If it doesn't accept a proton, it's not a base. Now, in this case, the hydroxide could actually accept a proton. If we had something that would donate protons, the hydroxide would accept one, becoming water, and the hydroxide would be a base. But we do not have any Bronsted-Lowry acids or bases here. No acids, no bases there. Zoinks. Zoinks. So the big summation is that we can only identify Bronsted-Lowry acids and bases in the context of a relationship, in the context of a reaction. Whoever gives the proton is the acid. Proton donor equals acid. Whoever accepts the proton is the base. Proton acceptor is a base. Easy breezy, right? We're going to practice identifying acids and bases now. We are only working with stuff on the reactant side. Who on the reactant side donates a proton? Hydrogen bromide. So, we're going to color code label this. So water is a Bl base. Oh, I forgot to be recording. Okay, so we've identified our acid and base. The acid is the thing that is going to donate a proton. The base is the thing that is going to accept a proton. So this is straightforward, right? You can identify these, I think. Okay. I want to ask you a question. Could bromide take back its proton? In theory, if you didn't know anything about electronegativity, it's a 1 minus ion. Can 1 minus ions ever pick up 1 plus ions? Sure. So bromide could, in theory, accept a proton. What would that make it? It would make it a base. So, what we call this is a conjugate base. Conjugate base. And for every acid, for every Bronsted-Lowry acid, there exists a conjugate base. Okay? For every Bronsted-Lowry acid, there exists a conjugate base. And basically, it's whatever is left of the acid after it donates its proton. Because it could take its gift back. Okay? So, you might suspect something about the hydronium. Could the hydronium give up that extra proton that it picked up? In theory, it could. I mean, it's got a +1 charge. It could be neutral if it would just give up that proton. Most things like to be neutral. Could it give up the proton? Yeah, it could. Which would make it what? An acid. Whoops. This is a conjugate acid. For every Bronsted-Lowry base, there is a conjugate acid. So Bronsted-Lowry acids and bases are always on the reactant side. The conjugate acids and bases are on the product side. Okay, so let's go down here and identify the conjugate base. The fluoride ion could take back its... The fluoride ion could hypothetically take back its proton, right? Okay, which would make it what? Conjugate base. For every acid, there is a conjugate base. Okay? Could the hydronium ion give up its proton? Yeah. Which makes it a conjugate acid. For every conjugate base, for every Bl base, there is a conjugate acid. Okay, these are called conjugate acid-base pairs. So for today, and I forgot to mention this, I've been reading about learning targets. Your learning targets for today, you need to be able, by the end of the day, to identify proton donors and acceptors. I think you're all pretty good at that. Name the Bronsted-Lowry acids and bases, which follows right from number 1. And identify conjugate acid and base pairs. Okay. So, what are the things that clue you in that something is a conjugate base? It's what's left over after the acid gets rid of its proton. So it's the butt end of the Bronsted-Lowry acid, as it were. Okay, so in our first example, who gives up a proton? H2O. So H2O is our... gives up the proton. It is the acid. If it is a proton donor, it is a Bronsted-Lowry acid. Okay. Who accepts the proton? Ammonia. So it is a Bronsted-Lowry base. Good. Okay. Who on the product side could, in theory, give up the extra proton that it's picked up? The ammonia, which makes this our conjugate. And I'm going to abbreviate that because it's really hard to write in this space. It's going to make our conjugate acid. Yeah, I'll fix that. No, because we've been doing our pairs in the same color. So, So we put a line connecting the pair, because we think about these things in terms of conjugate acid-base pairs. Okay, now, what on the reactant side could theoretically accept its proton back? The hydroxide ion. And that makes this the conjugate base. Okay? So there's always a pair. There are two pairs. Okay, let's look at the one below, which I think is actually a little bit trickier possibly. What compound on the reactant side donates a proton to somebody else? H2O again. Okay, so that makes that the Bl acid. Okay, so H2CO3 is our conjugate acid because it could theoretically give its proton back. Which of the things on the reactant side could theoretically reaccept or could take back the proton? The hydroxide ion. So that makes it our conjugate base. Okay, so there we have our two pairs. Does that make sense? Okay. So now we want to talk about the likelihood that that will happen. Remember our friends from the last slide? Hydrogen bromide, hydrogen fluoride. Few of you expressed some concerns about the willingness of hydrogen fluoride to really give up that proton. So this is akin, I'm going to make the Christmas gift metaphor for proton donation. I'm going to pause the recording. Depending on the sort of attraction of the recipient for the gift, it really changes the likelihood that that gift would be returned. So let's look at the hydrogen bromide, water, hydronium ion, bromide ion. What do you know about hydrogen bromide? It's a strong acid. It gets rid of its hydrogen, and it's happy to do so. It is a strong acid. Strong acid. This is a strong acid. What that means, that is on the list where you just kind of have to know those. Remember, of the hydrogen halides, 3 are strong, 1 is weak. So hydrogen chloride, hydrogen bromide, and hydrogen iodide are all strong, which leaves us with one weak thing that we're going to talk about shortly. Okay, so hydrogen bromide is a strong acid. It gives up that proton. It wants to give up that proton. It wants to act like an acid. It's not taking the proton back. It is absolutely not taking the proton back. This is David giving the fly rod to Clay. The bromide ion is not going to go back out and get it's not going to get its proton back. And wait, that analogy. It is unlikely that the bromide ion is going to reaccept its proton. Okay, so it's actually a weak conjugate base. It's a weak conjugate base. It's not likely to accept the proton back. Now, every time that your acid is a strong, every time your acid is a strong acid, your conjugate is a weak. Okay? If your acid is strong, your conjugate base is weak. If your Bl base is strong, then your conjugate acid is weak. Okay? Now, let's look at the hydrogen fluoride, the next example. What do you know about hydrogen fluoride? It's a weak acid. It does not really have a compelling reason to give up that proton. It likes the proton. This is David with the bagpipes. Okay? If it does actually give up, it doesn't have a strong reason to give them up. It's got a weak set of reasons to give them up. So once we have David over here sans bagpipes as the conjugate base, he's very likely to reclaim the bagpipes. Hey, if you're not using those, I'll take them back. Okay? So the fluoride ion is a strong conjugate base. It is very likely to reclaim its proton. Okay? With protons? No, there are strong. So here's the relationship that's a good question. No, the relationship between the Bronsted-Lowry acid and its conjugate base is universal. If your Bronsted-Lowry acid is strong, the conjugate base is weak.
So if it's not allied, how are we going to know it's strong?
This slide where it gets weird was just talking about the conjugate acid-base thing. And the last slide, and this is what we'll finish with, is the strength of the acid-base pairs. And that's what we just talked about. So if something is a strong acid, its conjugate will be weak. If it is weak, its conjugate will be strong. So we always have opposite pairs. And whichever, if we think about the hydrogen fluoride example, so HF plus H2O, because this one's weak, it's a reversible reaction. Because of the fact that this is weak and this is strong, equilibrium generally ends up on the side of the weak because the strong pushes it the way it wants to go. So the strong acid or strong base, the strong thing wins. So we end up with equilibrium on the side of the weak ones. Okay? That's where we're going to stop. You have some additional problems in the homework, and you're going to have a FIP quiz. Now, here's the FIP quiz. Tomorrow will be on identifying Bronsted-Lowry donors, acceptors, Bronsted-Lowry acids and bases, and acid-base pairs. Okay? I'm not going to expect that you can identify whether or not the Bronsted-Lowry acid is strong or weak. Okay? I'm not going to do that in the context of these. So.